Welcome to the forward error correction video. We are going to explore what is transmission error, what is forward error correction, FEC, error detection technique, error correction technique. Before we start this video, let's understand some basic terms. What is transmission error? Transmission error happens when data gets altered, lost, or corrupted during its journey from a sender to a receiver over a communication channel. For example, here sender sends data via a communication channel. At receiver end, their data was received, but there is an error. In fiber optic communication, data is sent as pulses of light inside a thin glass fiber. These light pulses bounce inside the fiber core and travel long distances with very little loss. In ideal condition, a bit of data would transit from fiber and be received out accurately at the receiver. Unfortunately, networks don't operate in an ideal world. Noise in the channel, signal distortion over long distances, hardware faults, synchronization issues, and environmental factors are causes to comes error in transmitted data. Single bit error, only one bit in the data unit changes. Burst error, 2 or more bits in the data unit changes. Why error correction is required? When transmitting high-speed broadband network, the data transmission reliability provided by the network may be lower than the reliability requested by an application. For achieving this, network must compensate for the difference in the bit loss rate. For improving reliability, 2 basic schemes are available: automatic repeat request, ARQ, and forward error correction, FEC. AQR scheme have been used for many years and is widely implemented. This technique uses a feedback channel between the receiver and the sender to request message retransmitted in case of errors are detected, as each request adds at least 1 round-trip time of latency. Forward error. Connection avoids the shortcomings of ARQ for high-bandwidth optical networks that required low delays. In FEC technique, redundant information is transmitted along with the original information. If some of the original data is lost or received error, the redundant information is used to reconstruct it. Let's explore what is forward error correction. FEC is a method of error control for data transmission, where the sender adds redundant data, error-correcting codes, to the original message. This allows the receiver to detect and correct errors without needing to ask the sender for retransmission. The addition contains sufficient information on the actual data to enable the FEC decoder at the receiver end to reconstruct the original message. The FEC decoder can identify the bits received in error and correct them. It then removes the redundant bits before passing the message to the upper layers of the network. Because the FEC decoder uses only the redundant bits to detect and correct errors, it does not request retransmission of the entire errored frame. Let's talk about majority rules. Majority rule is a simple error correction technique used in forward error correction. Each bit is transmitted multiple times, commonly in groups of 3, triplication. If an error occurs during transmission, the receiver compares each group. The value, 0 or 1, that appears most often in the group is considered correct. This method can detect and correct single-bit errors within each group. Here is an example. We want to send a data shekhar from computer A to computer B. We get the ASCII binary code for our data at computer A. Here is ASCII binary code for data shekhar. In majority rule, this process is completed in 3 steps. Step 1, replicate each bit 3 times, triplication. In this case, our first bit of data is S and its binary code is 010100011. As we are sending each bit 3 times, our first bit 0 became 000 and 1 become 111. Similarly, all bits are updated. This is called triplication. Step 2. Now, at the receiver side, we can see 3 bits are get corrupted. So we can see our original message is corrupted. In step 3, considering the majority rule of correction at the receiver. First error bit have 2 ones. This bit will be considered as 1. At 4th bit data 2 ones and 1 0 we received, so this bit will corrected as 1. Similarly, other error bits are also get corrected. Finally, we transferred data shekhar from sender computer A and we received error data at computer B. With the help of majority correction rule, we fix this corrupted data. Data is received at receiver. Let's explore one more error correction method, Hamming code method. A parity bit is an extra bit added to data to help detect errors during transmission. There are two types, even parity, total ones is even, and odd parity, total ones is odd. Even parity bit, the parity bit is set so the total number of ones, including the parity bit, is even. Example, 1011 data, 3 ones, so even parity bit, dagger 1. So total number of ones are now 4. Odd parity bit, the parity bit is set so the total number of ones, including the parity bit, is odd. Example, 1011 data, 3 ones, so odd parity bit, dagger 0. So total number of ones are now 3. Although there is no any direction for which parity bit method to be used, it is recommended that even parity is followed in industry. Only condition is sender and receiver both same parity bit method. Hamming code works on the principle of 2 rest to r, wash k plus r plus 1, where r swarm parity bits and k is data bits. Let's take an example. If data size is 4 bits, then how many parity bits are required for this data transmission? From equation, we can see for 4 bits of data, we need 3 parity bits. Back to our 4 bits data is 0110. We want to send this data along with parity bit and also see the position of all data bit and parity bits over the transmission. Remember, if we are sending 2 parity bits with data, then receiver must have 2 parity bits at their end. So, in this case, we are sending 3 parity bits with data, then receiver also required 3 parity bits data check. Possible combinations for 3 bits data are followed. This combination provides the details of parity bit in the data. Like first combination say 0 position. In this case, no error was detected over receiver end. Combination 1 says first bit is get corrupted. Similarly, all these combinations says specific bit data get corrupted. Here first in, first out, FIFO, is coming in the picture. It doesn't correct errors, it just preserves the order in which data is processed. Basically, when checking for errors at receiver end. When R3 checks, it check for bits higher for P1. When R2 checks, it check for bits P2. And finally, when R1 checks, it checks for P3. In other words, we can say that R3 judge for any bits, 1, 3, 5, 7 of P1 are corrupted or not. For R2, this looks for 2, 3, 6, 7. And finally, for R1, this look for 4, 5, 6, 7. Bits are corrupted or not. Considering all bits, first position, we get the correct position of parity bits. In this case, we get 1, 2, and 4. Bit position is reserved for parity bit in this 4-bit data transmission. Now, let's see how our 4 bits data get parity positions. For P1, we can check parity for position 3, 5, and 7. By default, we use even parity logic. So, we can see that odd number of ones are in all 3 bits, so we mark 1 for P1. For P2, we can check parity for position 3, 6, and 7. We can see that odd number of ones are in all 3 bits, so we mark 1 for P2. Finally, coming for P4, we can check parity for position 5, 6, and 7. We can see that even number of ones are in all 3 bits, so we mark 0 for P4. Now our 4 bits data 0110 is ready with parity bits 11001110 for transmission. This is how we use Hamming code method for sending and receiving data with parity bits. Before we close this, just take a quick look in comparison between majority rule and Hamming code method. Thanks for watching this video. Stay tuned for more videos like this one.